have had the opportunity to measure and study the characteristics of blast, the basic destructive force released by an atomic bomb, to study it in the course of 4 detonations over 2 types of targets, 3 different heights of bursts, and 3 different yields. The Tumbler operation provided good experimental data on which we can base new height of burst curves for operational use. These curves falling between the old theoretical curves and the data obtained during Buster, providing for the first time experimental proof of the advantage of detonating an atomic bomb high in the air when weak targets such as aircraft are involved. We also found that the normal cube root blast scaling laws developed from high explosive tests apply to the blast pressures from atomic weapons. A new phenomena which may account for the low pressures measured on previous tests was observed for the first time on the 4th shot of Tumbler, a so-called precursor pressure wave moving out from ground zero in advance of the incident shock wave from the bomb. This precursor wave may be caused by the intense thermal radiation released at detonation. We'll have to study, analyze, and cross-check, and then return to our outdoor laboratory again to proof-test our findings. But blast phenomena wasn't the only thing studied on Tumbler. Let's go back and take a look at some of the others. Before Tumbler, there was little information about the effects of blast on aircraft dispersed in the vicinity of the burst. We didn't know for sure how much blast pressure an aircraft could withstand and still take off on a mission. So we moved a variety of aircraft types into stations at various distances from ground zero. The aircraft themselves were positioned in a variety of orientations to the burst. Some faced directly into it, some directly away, some at oblique angles, some at right angles. Will orientation be a factor? If so, how much? Since a fighter is built to withstand greater load factors than a bomber, will the fighter sustain less damage? Will jet planes, which are built to withstand the great pressures of high speeds, sustain less damage than conventional aircraft? We're primarily attempting to define the damage area limits under the different conditions of detonation. So if a plane was not damaged on one shot, we moved it closer for the next shot in an effort to find the breaking point. Some aircraft themselves are instrumented to record the strains and pressures inflicted upon them. We're backing up the instrumentation in the planes with thermal measurement instruments near them on the ground. We have positioned some of the planes behind shields and revetments to help us analyze the value of passive defense for enemy aircraft and for our own planes. We're going to get a lot of valuable information, too, on the effort required to return aircraft to an operational status after exposure to a burst. Shot day. The effects of an atomic bomb on aircraft. After a shot, we're all anxious to get back to our test setups and see for ourselves what happened. The data is here. It only needs to be recovered and analyzed in order to be applied to the plans and problems of atomic warfare. Among many other things, we learned that bombers do receive more damage than fighters. Jet aircraft generally sustain less damage. Planes in a side orientation to the burst receive the greatest damage. In all cases, damage is closely related to the height of burst, distance from ground zero, and kiloton yield of the bomb. Planes in some cases can be returned to operational status after exposure to an atomic detonation. Some can go into operation immediately. Hopefully, this program will give our military planners a great deal of new and vitally important offensive and defensive information. While we're trying all the time to better our position and approach to offensive use of atomic weapons, We're trying just as hard in the other direction to learn all we can about protection and defense against effects of the bomb. Normally, in combat, when a man doesn't have something like a trench or a foxhole to seek shelter in, he takes advantage of whatever protection is available, such as a forest or heavy foliage. So we went to Mount Charleston near Las Vegas, selected and carefully removed some evergreen trees that were in perfect condition to bring to the test site. We've been making studies for years on the thermal characteristics in different forest situations. By pulling trees over, breaking them, and various other tests, we have developed some very reliable systems for estimating the static forces necessary to damage trees. Now we need to learn the reaction of trees to the dynamic forces and thermal radiation produced by atomic weapons. Once the trees arrived at the site on special trailers, they were carefully removed to minimize the amount of breakage and planted in concrete foundations at varying distances from ground zero. Since we know the breaking point of these trees pretty well, we're trying to place them in positions and at distances to measure how much the trees will bend under the shock wave forces. Then we know how much more it would take to break them. We're instrumenting the trees with strain gauges, scratch gauges, and other gauges. Some of our other trees are like something right out of science fiction. During the operation, they took on the nickname of lollipops. Actually, they're idealized tree models, consisting of flat metal plates mounted on steel beams. The lollipops are instrumented to help us determine the motion and bending strain on trees subjected to the fierce pressures in the shock wave. This combination of real and idealized model trees will also help us to get a good reading on the drag forces of tree crowns. Fires may be a discouraging factor too. So we're setting out a variety of things that could ignite and burn in a forest. These are known as forest fuels, materials that might carpet the floor of any forest, such as logs, pine needles, beech leaves, cheatgrass, moss, and fir needles. The blast and fire of an atomic bomb are even more dangerous in populated areas. So we're exposing specimens of common structural details, covered and uncovered wall angles, some bare, some exposed with materials that will ignite easily, approximating inflammable trash found in almost any urban area, plus various types of roofing. All of these structural components are without defects that would tend to cause them to ignite or burn. All of this to determine the vulnerability of building components to ignition and sustained burning from atomic weapons. We're also setting up cubicles or miniature buildings to relate the study even more specifically to the problems of a city exposed to an atomic bomb. To find out what ignites inside, we're installing various types of furnishings, such as wood tables and chairs. This project is looking for primary ignitions, not secondary ones from overturned stoves or damaged electrical circuits. We're also going to be able to study the interaction between thermal radiation and the blast wave, and the characteristics of the blast wave in spreading or putting out fires. Our forestry line is ready. Shot day. About shockwave effect on our trees, we learned that they are fairly flexible even against the dynamic force of the bomb. There was a minimum amount of breakage and little damage from flying missiles. However, all of our stations did not come out unscathed. We found that with trees in good condition, generally good thermal protection will be available, thus lowering the degree of burning and the ultimate area of damage. But a full evaluation of their blast protection or hazards will depend on more extensive tests in the future. Our fuel samples were upright to provide the most ideal conditions for igniting and to help us find the limits of the bomb's ability to start and blow out fires. It is only relatively close in that the shock wave blows out a fire. Our miniature buildings and structural specimens gave us valuable data and confirmed many predictions. Sustained burning will not occur if structures in good condition are beyond the primary blast area. After the heat from the bomb has diminished, the fire will generally go out. There would probably be some ignitions through open and broken windows. Then we set out to broaden the foundation of knowledge on which we can reliably base troop participation in atomic warfare. First of all, we want to learn more about the effect of atomic bombs on the combat tools of ground troops. So we're going to let the blast work over a wide range of implements used by soldiers in the field. A cross-section of everything that rolls or shoots will be exposed in a variety of orientations to the bursts and at several distances from the detonation, from large artillery units and heavy machine guns to light weapon emplacements.